You mean the fourth one? The first referee? Oh, the first referee. Ah, okay. I used to.
Can you all see this size of font? Okay. Hello, everyone. Good morning. Welcome to the Hydrocarbon Production and Process Engineering module, which will take place all this semester, and we are basically going to meet every Monday from 9 to 11. We will normally have more or less what I aim to be a 45 to 50-minute lecture first, and then we'll take a break and do the second part of it. My name is Sharon Velasquez, and I'm based here in Merskert on the 3rd floor. My office is in C315. In case you have any questions or any need of any help during this term, please don't hesitate to contact me. Also try to manage your time, learn as we are basically introducing you these concepts, and don't wait until the end of the semester to contact me or to ask me questions, because then it gets very complicated. This part of the module is going to be given as well from a lecturer that comes from industry, in this case for Benspen, which is a very big global company that works in different petrochemical sites, and they provide project management and as well as engineering solutions. So Nigel Curson has been given this lecture for a long time, and he's Vice President of Excellence Engineering, and he basically advises all the regional centers on different challenges that they have during the petrochemical operations. So he will basically come to give you part of the lectures. And because of his timetable, it's going to be, I think, 1 or 2 sessions where we're going to be here for a whole day, and he will give you all the concepts from that, as he's unable to come on a weekly basis as I do. But I think that is still valuable for him to come and give you all this from another perspective, which is the industry. So here is his email as well. And the aims of these modules basically is to increase your understanding of hydrocarbon production, to learn about the single phase flow of gases and liquids in pipes, so a little bit of fluid mechanics, how whilst we extract oil, one of the most important things, or the first phenomena that will occur, is transport of this oil through a pipeline. And then, well, first we will start working on single phases, taking into account that the pipeline only receives a gas or a liquid, and then after that we'll go into multi-phase, a little bit more going into reality, where we have a gas and a liquid mixture going through a pipeline. And something very important are the engineering thermodynamics for the design of flow processes. So here thermodynamics is going to be applicable to several parts of the module. So we actually will start this part today. The assessment will consist of an exam, which you will have at the end of the semester, and it will be a 3-hour exam, and you will have to select 3 questions out of 5, and these 3 questions will have a series of sub-questions. We will include theory concepts as well as a lot of problems for you to solve. We will also have a coursework which will come to 25%, and this will be basically an example of one of the processes that we see, whether it's multi-phase flow. It will essentially be just the mass and energy balances and calculation of what happens around a petrochemical site, and this will give you the 25% of the marks to have the 100%. So the references that I will recommend is basically Introduction to Chemical Engineering Thermodynamics, which you can find in the Robinson library, and I think they have several copies of this one for you to read. Sandler as well, Chemical and Biochemical Engineering and Thermodynamics, which these two give you the theory concepts of what we are learning in here. They are applicable to any type of process in chemical engineering, not only petrochemical sites, but the fundamental theory is explained there. And then Kraut is especially useful for the multi-phase flow handbook, and not only that, I give you that reference, but there are several references that also talk about multi-phase flow, especially on fluid mechanics and through pipelines, chemical engineering books. So here we have a little bit more specifics on the timetable and how many hours we expect to take to any one of the processes. So here I have divided the timetable really in two, the parts that I will be showing you and the parts that Nigel Corson will basically discuss with you. So we will start with looking at equations of state and the relationship to the physical properties of hydrocarbons. So obviously that will be the first part in order to determine some specific properties that help us throughout the calculations in a petrochemical plant, flow processes, properties of multi-component mixtures, and then single phase and either gas or liquid hydrocarbon flow in pipelines, hydrocarbon dew point control, and here we will go through the specifics of distillation columns and how we design a distillation column, which is basically one of the key processes in a petrochemical plant, and as well as talking of gas and liquid dehydration, and finally carbon dioxide and sulfuric acid removal, which are key contaminants that normally are taken out from this type of fluids. So Nigel will give you the basis of multi-flow phenomena and especially correlations that are used in industry in order to explain this type of flow systems. Heat transfer. I will also go and discuss a little bit about heat exchangers and how thermodynamic concepts are applicable to these type of things, but he will give you as well information on heat transfer. Talk about wax, hydritis, and corrosion, some of the challenges that we have in petrochemical sites, transients, pumps and compressors, optimization and field development, and pressure protection and leak detection. Okay, so some of these concepts we will also discuss during our lectures, but I think that he will complement this knowledge as well as give the industrial perspective. Finally, towards the end of the module, we will have a practical demonstration, and this is for you to get familiar with a software that is installed and available in all the chemical engineering computing cluster, which is HYSYS, developed by ASPED, and we'll basically go through, it's going to be just a 2 hours practical, and we'll go through the demonstration on how we use this type of software and how we perform these calculations with the aid of these modeling tools. The lecture notes are uploaded in Blackboard, so you're able to basically retrieve the information from there. And also there is a lot of information included, the manuals of HYSYS operation, in case you are curious and would like to start exploring it by yourself. Right? So so here we basically have what we will try to calculate and to understand throughout the length of this module. So we typically have a gas reservoir, and after a gas reservoir, we basically, through the extraction of this energy accumulation in this fluid, the first thing that we will do is the gas reservoir will go through a pipeline, and we will have a gas and liquid separator. We separate the gas and the liquid fractions, and we basically provide some energy and some heat to them through heat exchangers and a compressor in the terms of the gas, and the liquid through a heat exchanger and a pump. Okay? So in this case, we basically, in this system, we are providing changes in temperature and pressure. And throughout all the length of the pipeline, there will be also changes in temperature and pressure. This will affect the properties of the fluid going through the system, in this case, the petroleum fuel. And throughout the knowledge of thermodynamics, we are able to correlate the relationship between this heat flow and the work, right? So thermodynamics derives from the word that says thermo, changes in temperature, such as heat flow, and dynamics. Dynamics refers to fluid, to mechanical engineering, to mechanical process, and basically work. So thermodynamics corresponds to the change, or initially started as the change of heat to work, right? And this is applicable throughout the whole system. The whole system will basically have, as the fluid goes through it, a change in temperature, pressure. It may also have a change in volume, but as we define temperature and pressure, we can also inherently guess volume through several equations of state, and therefore we need certain correlations, certain mathematical expressions that help us understand this process by theory. So we normally want to describe this process. We said that we want to know how the temperature and pressure changes in this process, and this is normally due to two key concepts, the enthalpy and the entropy. And this leads us into looking at the first law of thermodynamics. Okay? So who can tell me what is the first law of thermodynamics? Try to remember.
If A, B, C are three bodies, then he transferred from A to B, B to C, and C to A remains constant.
Okay, yes. Yes, very mathematically given through constants and everything. But basically, the first law of thermodynamics is the law of conservation of energy. Right? So, in this law, what it states is that although energy assumes many forms, right, given as you were saying heat, a type of energy, it could also be given as work, another type of energy, as electricity, another type of energy. It will remain constant, and while the energy disappears from one system, it will immediately appear in another system. Okay? So, this first law of thermodynamics can be explained through this. The delta energy of a system plus the delta energy of surroundings equals 0. Right? So that will mean the energy of the system will equal the energy of the surroundings. Law of conservation of energy. So in this case, this type of first law of thermodynamics was derived from the operation of steam engines. Okay? So the first thing that we saw and we wanted to explain in steam engines is the fact that we are transforming heat energy into work energy and how this was happening. So normally this heat and work energy will derive from the energy of the surroundings. So the energy of the surroundings is normally explained as changes in the heat, and heat normally is denoted by Q, or changes in work. And this can be either positive or negative, depending how the surroundings are either gaining heat or losing work or gaining work. So from this equation, we can say that the energy of the system will be equal to heat plus work. Normally, we take the positive sign as convention, right? But they can be either positive or negative. So therefore, the energy of a system will be equal to the heat of the surroundings plus the work of the surroundings. Now, we can take two types of systems. Let's have a look first at a closed system, and then we will have a look at an open system and how this first law of thermodynamics will apply to these two. So a closed system, we will define it as a system that is completely isolated and there is no energy transfer between that system and the surroundings. So that means that the mass is constant. So we have put a material or a fluid inside a vessel and we are not doing anything with it. Okay? So in this case, in a closed system, we introduce what we called the internal energy. So the only changes, since there is no surroundings, the only changes will be derived by the fluid that is inside the container. And this is normally explained in chemical engineering as the U. And changes in the U are changes within the internal energy of the system. So this internal energy of the system will be equal to changes of heat and work inside the system as well. Right? So in this case, we use U, which is a form of energy known as internal energy of a system, and it is an intrinsic property. So we will later give an example of an intrinsic property, but it's a property that is defined by a point of reference normally. So in this case, we can say that the changes in the internal energy will be equal to the changes in the heat plus the changes in work. And this we are referring to a fluid that is contained in a vessel and is not involved in any motion, because there are other types of energy that can also affect this closed system. If, for instance, the fluid was moving, there will be kinetic energy and other types of energy that will be influencing that. So we can say this type of equation if there is no motion. Okay, and normally the internal energy in those systems will be a function of the temperature. Why? Because the internal energy of a fluid will a lot of it will derive from the molecules. Any type of fluid, any type of element will have a series of molecules, and these molecules all the time are moving, right? So if we have hydrogen, water, oxygen, we have molecules moving inside a system. So these molecules and the movement of the molecules is what produces the internal energy of the system. So if the molecules move very slowly, that means that the fluid in itself will have a low internal energy. And if the movement of the molecules move really fast, that means that the fluid by itself will have a high internal energy. So what will influence the movement of these molecules? Something that influences is temperature. So if we increase the temperature of the system, the molecules suddenly start to move a lot faster. If we decrease the temperature of the system, of any fluid, the molecules start to move slower. And that will inherently affect the internal energy. So normally at low temperatures, any type of fluid will have a low internal energy. And at high temperatures, any type of fluid will have a high internal energy. So in this case, let's define a reversible process and how this affect work. Okay, so in this case, a reversible process, what will be a reversible process? Yes, that's the reverse of heating. No? A reversible process will be that an explanation. But physically or mathematical, in order to have this reversible process, that means that we move from one condition to the other, and we are able to do the opposite and arrive to the same place that we were at. So that means if we move from one energy to the other, then we are able to come back in there. Here in Earth, this is impossible because we always have an efficiency of the system. Okay, so in non-ideal place, a non-ideal concept, we will have an efficiency of the system, therefore we will have losses in the system, and it will be very difficult to have a reversible process. However, for a lot of calculations, we will use the reversibility concept to help us understand and simplify the calculations. Otherwise, calculations will become too complex, and therefore it will be very difficult to define the system. So something that engineers use a lot is basically said that the process is reversible, therefore we are idealizing the process, we're saying there are no efficiency losses, which is a very big assumption for us, but it helps us a lot in our calculations. So the reversibility of the process, there are different types of assumptions that are normally taken, but one of the most important ones is assuming that there is no friction. That is a frictionless process. And if we assume that there is no friction, which is most of the energy that is lost is through friction, then we are sort of saying that is a process that will go any way without losing energy into the system. Okay, so in this case, another thing that we can assume, so these are some assumptions: the reversibility of the process, defining that the process is frictionless, and another assumption that we can assume is equilibrium. And this is very useful when we are talking about chemical reactions. Perhaps in here we are not going to look into reactor systems, but thermodynamics are also applicable to chemical reactions, and that help us to separate the chemical reaction from the thermodynamic properties. So in here we are saying that in a chemical reaction what happens is that we have two compounds, let's say A and B, and then we mix these two compounds and we produce a new compound. Let's say we have hydrogen and oxygen, we mix them together, we produce water. So therefore, the properties will change when we have the water molecule, where molecules are close together, than if we have hydrogen and oxygen separate. For example, water is a liquid. Normally liquids, the molecules are closer together, and therefore the properties doesn't change a lot. They can be treated as incompressible. While hydrogen is a gas and oxygen is a gas, they are far away together, the molecules move, and therefore they are incompressible. So we can see how this chemical reaction is affecting the properties of the system. Since we want to explain the system thermodynamically, and we don't want to consider these changes because of the reaction, we consider equilibrium. And equilibrium is saying it doesn't matter whether hydrogen and oxygen are far away or close together, they are in equilibrium, and therefore they will have the same thermodynamic properties. And this is also another big assumption, but that helps us simplify the calculations as well, and help us work in thermodynamics with disregarding the chemical reaction that is also affecting the system, and concentrate on this part. So in this case, thermal equilibrium is also something that we consider in thermodynamics in the first law, and this says that all forces are in exact balance. Okay, so we're trying to take out and say, okay, let's have a look at thermal equilibrium. So the work for a mechanically reversible closed system is given by the following equation. dW equals minus PD and the changes in volume. Right? So this is basically taking into account the definition of a force. So a force, the power will be force times area. Okay, the power of a system is force times area. In this case, the force will be pressure, and we take the system in terms of volume, the changes in volume. And this comes from the fact that we have a piston, and then we move this piston by changing the volume of here through a certain process, and that will basically move a wheel or something that we have in here, and will produce changes in work. So in this case, if we have 4 n moles of a fluid in a closed system, we can say that n, and we said that we will have the internal energy. So the changes in internal energy for n moles, and moles is a chemical engineering term which defines the concentration of a compound. And in this case, basically, this is applicable to work in moles. We always want to work in mass, but moles normally are useful when we are talking about a chemical reaction as well. So we will standardize it to moles in order to take into account, to take out the molecular weight changes. And then we will have the changes in of a known quantity of internal energy will be equal to dq plus dw, okay, which was what we defined previously. But in here, if the process occurs, we can then change this to this expression, right? Because work was defined in here. So if the process occurs at constant volume, therefore the changes in constant volume will be 0, and du will be equal to dq, okay, to the changes of heat as well. And from the derivation of this equation, we can take q equals at n delta u. Okay, so the heat flow in this system will be derived from the changes in internal energy of the system if we have a constant volume, right? So what happens if we have a constant pressure? So let's come back to the equation. dq equals to dnu plus P and the changes in volume. So I'm just changing a little bit the order of the equation, but I'm changing it because I want to explain something. So this can be basically rearranged to dNu plus PV. So here we will have, when we had the constant volume, we were able to eliminate that and say dq equals changes in Q will be equal to changes in internal energy. If we have a constant pressure, then it will be equal to changes in internal energy plus changes in the work. Okay? So this, since this expression U plus V, since we are using it over and over in thermodynamics, we created a new thermodynamic property and we called it the enthalpy. And that's how the enthalpy was created, basically. Okay? So instead of saying U plus PV, we say H. Who has used the enthalpy before for calculation? Done mass and energy balances, you will have used the enthalpy, right? So this is how the enthalpy was derived, and therefore we define the enthalpy as U plus PV, right? As we mentioned in here. And sorry, I'm going to go a little bit on this side, and therefore we can say that dq equals dnh and q equals n delta h, and that's for a closed system. So in a closed system at constant volume, q equals delta u. At constant pressure, Q equals delta H. And delta H is only, say, internal energy plus PV. Okay, so it's always internal energy plus PV or internal energy, right? So now let's have a look at, well, here we can also explain the heat capacity, which is basically a new property that was defined. The heat capacity is, as its name say, the capacity of energy that has a certain fluid. And in here we can define heat capacity at constant volume, at heat capacity at constant pressure. And at constant pressure, Cp will be equal to dH over dt at constant pressure. Okay? So if we define that Q equals N delta H, Q will be equal to N, and to the changes from temperature 1 to temperature 2, Cp dt. So we can define delta H as Cp dt. And Cp will be the heat capacity of a system, and normally we define that for several systems. It has been defined and it can be found in tables, or sometimes it can be found as a linear equation that is variable to temperature. Okay, Cp can be a correlation of the changes of the properties of the Cp based on the changes in temperature. So now if we have a control volume, so let's say for an open system, in an open system we will basically have an inlet and an outlet, okay? And in here we need to define two things before looking into the energy balance. We will have to define the mass balance and then after the energy balance. So for the mass balance we will refer, so let's say we have M1 and M2. what time is it? Okay, can somebody tell me when it's 10 to 10? 7. Okay, so we will have M1 and M2. So in this case, we have a control system, but we have an open system. Therefore, we have an input and an output. Okay. So in this case, for the mass balance, we will refer to the continuity equation in order to explain that. And the continuity equation basically tells us, in this case, is the mass that goes out will be equal to the mass that goes in. Now, the mass is defined. Mass could be the density times the velocity times the area, okay, of the system. So mass that goes in equals mass that goes out, and that's it. Now, in order to provide the energy balance of the equation, we will look again at changes in internal energy. Will be equal to the changes of the energies of the system. In this case, we will have enthalpy, the kinetic energy, or the potential energy, times the mass of the system, Fs equals Q plus W. Okay? So here we are considering in this equation the changes in energy of the through time will be equal to the changes in enthalpy plus the changes in kinetical energy plus the changes in potential energy for any given mass. And this will be equal to the external changes of heat and work that we defined previously. Okay? So for Fs is just flow system. So we are just generalizing it for any type of input, any type of output. We can have M1, M2 going in, M3 going out, and so on. So the energy balance for a system that only has one input and one output, therefore, will be defined as delta H equals, and it's a steady state. So this is the energy balance. So for a steady state process with one entrance and one exit, we will have delta H equals plus delta U squared over 2 plus G delta Z equals Q plus WS. Okay? So we don't have in this case, it's a steady state process, so therefore the accumulation goes out. This get crossed, this is equals to 0, and we end up with this equation equals Q plus WS. Right? Is this clear? So we're taking out the accumulation effect of the internal energy. Internal energy is all the energy that stays in the fluid, but since this is a steady state process, everything that goes in goes out, therefore no accumulation. And this is the sort of, let's say, general equation for the first law of thermodynamics. So let's go back. So what will be the most important term of the first law of thermodynamics? Can you tell me? The most important term?
Conservation of energy.
Conservation of energy, the concept, and the variable?
Internal energy.
Internal energy, definition of internal energy, and definition of enthalpy. Okay? So these will be the variables that we define in the first law of thermodynamics. And this is used in engineering systems such as the petrochemical extraction in order to help us define changes in temperature and pressure throughout the system. So this is what we want and how it affects the fluid that is going through, how the conduct energy balances in the system. Now let's now have a look at the second law of thermodynamics, right? Second law of thermodynamics. Who can tell me what is the second law of thermodynamics? Any ideas? Anything? what comes to you when we say second law of thermodynamics? Difficult concept? What is the first thing that comes to you when I say second law of thermodynamics?
Entropy.
Entropy, right? So second law of thermodynamics, I think that if something stick to us was entropy, something to do with entropy, right? So this type of second law of thermodynamics comes in order to further explain the first law of thermodynamics. So the first thing that we defined in the first law of thermodynamics was the assumption of no friction, the ideality of the system, conservation of energy. Nothing happens. The system is irreversible, therefore there's no loss of energy. However, we know that that's not the reality. Processes have either a direction, they are processes that cannot be reversible, and processes are not 100% efficient. We always lose energy. So they say, hang on, the first law of thermodynamics cannot explain everything. There's something that we lose. How do we explain what we are losing in this system? Through efficiency? Well, not good enough. We need something more stronger than efficiency. Let's define entropy. So entropy defines everything that we lose in the system and we cannot explain. It's very useful for engineers. Let's name it entropy, we cannot explain it. And we could explain it, but through very difficult fluid mechanics calculations, which will go into very complex calculations. And since we don't want to go into very complex calculations going into the fluid mechanics of the system, we define entropy. So, in this case, the second law of thermodynamics, what it came from is basically we're trying to define what goes from a ordered state to a more disordered state. Okay? So we go from an ordered state to a more disordered state. And let's have a look if we can sort of understand that. Okay. So what it says is that most of the processes that occur spontaneously go always from an ordered state to a disordered state. For example, if I have this pen here, can you all see this pen? Here it is in an ordered state. It is just steady here without moving. If I start moving it closely like that, okay, then I'm trying to replicate an ordered state. I'm trying to be very precise and continue in an ordered state. And if you were to record me at this point and play me in the reverse, let's do backwards, and I continue doing this so on and so on, could you tell if I was going in the reverse way or if I was going in the forward way? No. It will be very difficult because I'm always doing the same movement. So you will have to take other reference, perhaps something moving behind me, in order to say, oh, what is the way that this is going on, right? So in this case, when I'm doing this, I'm trying to minimize entropy. I'm trying to let not entropy exist. However, entropy exists because all the energy, I'm losing heat here, I'm getting hot because this is quite difficult, and therefore I'm actually losing energy that you cannot see because I want to do this process. If I take this pen and then I throw it like that, and you were to play me in the reverse way, would you be able to define which was the way that was the forward and reverse way? Yes, right? Unless you thought that the pen going to my hand will spontaneously occur, which cannot occur so far, and if somebody finds out, I think it will be a very big discovery. At least on Earth, this cannot occur. So in here, what I did is I had potential energy. The pen moved and converted the energy into kinetic energy using the gravity of the system. And suddenly it went into the floor and it dissipated the energy. Energy that was ordered, that was going that way, went to all the space. And all the energy that was dissipated was a movement of entropy. So the kinetic energy was dissipated as entropy, and the energy was lost as that, and the pen was resting at the bottom. And this process cannot be reversed by itself. Therefore, entropy always, in order to occur spontaneously, goes forward. If I wanted to reverse the process, I have to invest energy into the process, go down, and take out the pen. The pen won't go to my hand by itself. And that means that I'm using energy in order to reverse the entropy process, right? So in the law of thermodynamics, what it says, no apparatus can operate in such a way that its only effect is to convert heat absorbed by a system completely into work done by the system. So the efficiency of the system will lose energy as a form of entropy, of energy we cannot recover. And no process is, sorry? Yeah? Ah, okay. Thank you. I need time to absorb this, I suppose. Let's take a 10 minutes break and we will continue.
Hello. I was wondering what parts of this would go up in Blackboard?
Huh?
What parts of this would go up in Blackboard?
Well, this is recorded, I think.
Okay, so it's going up a recap then, all the slides.
Recap, yes.
Okay. There won't be any slides or anything, it'll just be recap.
For first and second law, no. But after that, I will use slides.
Okay.
Yes,
Okay.
it's just the basic.
They forgot to come on card, so it's getting my call there.
Oh, right. I don't know what you do in that case. Do you know? Have you had that problem before or not? Okay, so write down your name and then if you want to write down your name here in case there are any problems there. Bien, sí.
¿De dónde es?
De México. Ah, qué gusto.
¿De qué parte?
Bueno, nací en Veracruz, pero soy de México. ¿Y tú? Ah, qué bueno. Ah, qué bueno, Villahermosa. Creo que Pespen también está en Villahermosa, ¿lo conoces?
Lo movieron a Ciudad del Carmen.
Ah, lo movieron a Ciudad del Carmen.
A ver si nos toca. Regresando para allá.
Ah,
Sí.
¿Y te veniste a hacer la maestría?
Sí, el CONACYT me mandó.
Ah, qué bueno.
Sí, ya pues apliqué y me aceptaron.
Ah, ¿dónde estudiaste?
En el Tecnológico de Villahermosa.
En el
Sí,
Tecnológico de Villahermosa. Ah,
Y hice también verano científico en la UAM. ¿Dónde estudió usted?
yo estudié en La Salle y en la UNAM. Sí, en la Ciudad de México.
Sí, te digo, hice verano científico, estuve 2 meses allá, así que más o menos la conozco.
Ah, qué bueno.
Sí, pues es un gusto tenerla como está.
Igualmente, ¿qué estudiaste?
Ingeniería química.
Ingeniería
Me
química.
recuerdo el tercer semestre, todo esto lo vi en el tercer semestre, pero ya tiene años, como 4 años que no lo veo.
No, bueno, pues.
Pero yo con una repasada.
Sí, con una repasada. ¿Cómo te llamas?
Ángel.
Ángel, ¿qué tal? ¿Cómo te ha gustado mi casa?
Bastante, es muy frío.
Ah, ahorita sí.
¿Cuánto tiempo lleva usted por acá, mañana?
Yo ya 10 años.
But I've got all the papers I need.
Ya.
I just need to read them.
Ya es un
¿No extraña
tiempo.
por allá?
Sí, pues voy a ver a mi familia muy seguido y todo, y colaboro mucho con la UNAM. Tengo proyectos de investigación. Mi área de estudio es biocombustibles, de hecho, investigación, y estamos trabajando en microalgas. Sí. ¿Tú qué quieres irte después de eso? ¿Ir a la industria?
Sí. Pues ya me toca conseguir algo de experiencia profesional, porque pues ya voy para 25 años y todavía
Ahorita en México está difícil, ¿no?
I just have to read it everywhere. It literally set me off.
A ver qué tal está. ¿Qué tal? ¿Has visto el área de petroquímica cómo está en México? Porque ahorita con todo lo de
pues ahorita hay una empresa que lleva un proyecto muy grande ahorita en Tireno 21, pero todavía no ha arrancado.
¿El Tirana 21 es de Pemex o de quién es?
No, es una empresa brasileña, Brasil. Sí. Y de esa
¿Pero es
Brasil.
producción de Tireno a partir de biocombustibles o...?
No, está ahí en el mina Titán.
Ah, mira,
Pues como por eso son rumbos por ahí. Pero la verdad es que me llama más, yo estoy haciendo pipeline.
te gusta más plataformas.
Con todas las plataformas, me llama más function. Sí, no me llama tanto la atención. A ver, donde nos toca
Sí,
ya.
a ver, bueno, pues estamos en contacto para cualquier cosa que necesites. Sí, igualmente, que estés muy bien.
Yeah, he literally sent it out. Hopefully I can download it. It's like 17 MB. What did you find out? My literature review, I'm just showing him like what the guy sent me from the company, from Rosen. But he literally sent us every file that he wanted to read, but he just went off and why is it better? Man's 4G, how can
Have you ever used 4G?
it's not good in comparison. No, it's just downloading, that's the Still searching. Yeah, okay.
The one you have to log in.
It's my what? My login?
Not a new login.
I have to look from my email. No, because I don't know the actual username, so I have to look at it anywhere.
Well, next time you
Yeah, you can change the password, but you can't change the username. So I have to, so I can't remember the username.
you memorize it. So
No, but it'd be so
I know, but you memorize so much stuff for the exam that you can memorize.
I can easily if I wanted to, but I just haven't that's the point. I've never read anything useful. But and literature review is about 20 pages. It's about, I think it's maximum 20 pages. But I'm so looking forward to it.
What should I?
What's your topic? And obviously that. So explain the process, how it came about, the chemical format and why it sticks. That's a good choice. Any recommendations? Yeah, of course. Of course, he's going to apply.
Okay, 10 o'clock. We'll continue. Right, so we define what entropy means. So I hope everyone now is clear to what entropy explains. So again, this property called entropy is an intrinsic property of the system. So that will be defined, that entropy normally is defined looking at the whole system and how it changes with respect to others. We can define whether an entropy system will be for a reversible or an irreversible process. So if we have the entropy, the initial entropy of the system minus the final entropy of the system, and this is equals to 0, that means that the entropy of the system at the beginning equals the entropy of the system at the fast, then that will define a reversible process. Okay? So for any reversible process, delta S total will be equal to 0. And this is very useful in calculation, especially when we look into compressors. Most of the times when we do calculations on compressors, we always assume that it's an isentropic process, that entropy doesn't change throughout time. For processes which are irreversible, the entropy will always be positive in order for the process to occur spontaneously. If the entropy is negative, that means that the process cannot occur spontaneously and will need energy to be invested into the process in order to occur. Another example that helps us define entropy is, for example, when we produce in electrochemistry, when we produce electricity out of a chemical reaction. Okay, so normally the way forward, we can produce electricity very easily through a spontaneous chemical reaction, but it's very difficult to do the opposite way, spontaneously. Okay, again, this defines also if we go from thermal energy to work, we can easily convert thermal energy to work, but to do the reverse process, work into thermal energy, is very difficult to convert. Right? So thermal energy to work, we always have a positive entropy, and work to thermal energy, we will have a negative delta S, telling us that that process is inexistent if we don't do something else apart from that process. Is that clear? Right. So again, we can do energy balances taking into account the entropy, the same way as we did for enthalpy for the first law. And here we will have the net rate of change in entropy in a flowing system, plus the change in the control volume, plus the change on the surroundings will be the total rate of entropy regeneration. And that's basically what helps us define entropy. And entropy, the change of entropy, will be derived from this equation. We will have, in this case, the Cp over T dt, the influence of temperature, the changes in temperature of the system, and the changes in volume against temperature in the system. Right, so it resembles the enthalpy equation. However, it has a higher temperature effect on the system, which is reflected by this input of variables. Right, so now we have seen how enthalpy and entropy, the concepts that come from the first and second law of thermodynamics. And now we will have to look into how they change the pressure and temperature of a given system. So here we'll refer to the enthalpy curve, and this will help us look how the changes in enthalpy, temperature and pressure changes the properties of a fluid. So this is a 3D chart. And we normally in textbooks find 2D charts where we have the approximations of the changes of pressure against enthalpy, pressure and temperature, and so on. So let's have a look what can we see in this chart. So basically in this chart we can see that we will have two parts of the chart that define the state of the fluid. In this case, if we have normally low pressures and low enthalpies and low temperatures, most of the fluid will be in liquid form. Okay? So as the pressure increases, there are very small changes of enthalpy normally. So normally this will remain, we can assume that it remains constant. But as the temperature changes, the enthalpy will start to increase. Right? So as we start to heat the fluid and increase the temperature, the enthalpy will start to increase, and therefore it will affect the fluid and will make them change of state. So at a given temperature, we will have a phase change from the liquid to the vapor. So the liquid will start to boil and will now form gas particles known as a vapor. So the division between the liquid and the vapor is the saturation line. And here is when the enthalpy has, if you see, there is a change of the slope in the enthalpy, and that's basically the energy that is needed in order to do the phase change of the fluid. And this is known as the enthalpy change on vaporization. And that's basically the energy that is taken by the molecule, such as the internal energy, in order to start moving faster, 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 until basically the fluid is converted from a liquid into a vapor. And this saturation line will help us define what is the state of the fluid and how much energy is required in the fluid in order to change its state. So this will be the enthalpy changes. And here we have basically the heat exchangers, and this will be applicable to the heat exchangers. And in this case, if we want to, let's say, if we have a vapor and we want to decrease the the temperature, how much water will be needed in order to do that. Or if we want to increase its temperature and have a superheated vapor, then how much energy is needed in order to do that and help us obtain the Q in here. So let's have a look. If we have, for example, a fluid with a certain pressure and a temperature, which is located in A, and we start increasing the temperature, we can treat this increase in different phases. From A to B, we will have the sensible heating of the liquid, so that means that you are basically not changing the phase of the liquid, just invested energy in order to increase its internal energy. And from here, we will then, from B to C, we arrive to the saturation line, which is when we have the first boiling point of the system, and we will start to increase the heat of the system whilst it converts from a liquid to a vapor. And this is called as the latent heating. And then we obtain a vapor, and if we want to further increase the temperature of this vapor, we will go into something that is sensible heating, where we increase the temperature of the vapor of the gas and then arrive to the final temperature that we wanted to obtain, or the properties, the type of system we wanted to obtain, and we can therefore calculate how much heat was needed in order to obtain this system. So how will the enthalpy changes affect the work that is done in the system? So in here, when we have a substance and we want to produce work, there are two things that have happened: the changes in pressure and changes in temperature. Normally, the changes in temperature are quite low when talking about liquids. However, they become significant as we do work with gases. So, for example, here we have an explanation of a system A to B, which refers to the pumping of a liquid. We increase the pressure of the liquid in order to pump it, and we can see that there is a small change on temperature, but throughout the system, and no change in volume. Now, if we try to do the same in the compression of a gas, then since this is an incompressible fluid, we will have a compressible fluid, we will have a volume change, and therefore we can see that going from C to D will imply a temperature change as well as a pressure change. As we move to a higher pressure, then the line is not straightforward. It doesn't move as in the same direction as the pressure, but they diverge in certain way, explaining the changes in temperature that happen as well in the fluid. So therefore, increasing the pressure of a liquid will have less changes in temperature than increasing the pressure of a gas. Okay. And then if we do the reversible way of the system, then reducing the pressure of a gas, such as in the operation of a turbine, will inherently decrease the temperature of that gas. So for these reasons, whenever we are pumping water or we are pumping a liquid, it's very unlikely that you will have a heat exchanger next to it, because the temperature changes are quite small. However, in compressors, most of the compressors come with a heat exchanger, because the changes are quite high, and therefore we'll need to decrease the temperature in order to control the system. So here again is going back to the equation that we saw, that in thermodynamic theory we are able to define the changes in temperature and pressure on the system according to the following equation. In order to apply this equation, we have to know the heat capacity of the fluid and how the volume pressure and temperature of the fluid are related. So we have here the volume, changes in volume with respect to temperature, the temperature effect, and the changes in pressure. For a liquid, normally we consider this to be incompressible, therefore there are no changes in volume with respect to temperature, and this part can go out, and therefore we'll have delta H equals Cp dt, delta T, for liquids. However, for gases, we'll need to take into account these effects on temperature and pressure, as we have just seen in the chart, how pressure changes temperature, and this has to be taken into account. And therefore, we will need to take a relationship that help us. Here we have, we are trying to derive volume against temperature, so we need a relationship that help us define volumes as a function of temperature. And for this reason, we use equation of state. So which is the most basic equation of state that we use in compressible fluids?
Ideal gas?
The ideal gas law. Okay, so that will be the most simple one that we'll use in order to replace this volume term, have it against temperature and pressure, and be able to solve this equation. Okay. So all relationships between pressure, volume, and temperature of a substance are called an equation of state. And for gases with pressures up to 500 kilopascals, so 5 times atmospheric pressure, we can use the ideal gas law. And in the ideal gas law, we have use a constant which is called R, and this constant normally has been approximated through empirical data and has shown good relationship to explain the theory. And basically, this is 8.314 joules per mole Kelvin. Normally, this number will change according to the units, but in SI forms, we take this number, and we always express, when using this relationship, temperature as kelvins. In here, M will be called the molar mass, and the units are kilograms per mole. And this is basically referring to the molecular weight of the system. The pressure in here will be in pascals, Newton per meter square, and the volume in cubic meters per kilogram, and the temperature in Kelvin, in order for this constant to be valid. If the units are different, then this constant will have to change. Now, this is all well for ideal gases if we work at at pressures up to 500 kilopascals. However, if we work at higher pressures, we are not able to directly use the ideal gas law. So we'll have to use approximations. We take into account other changes in the system. In this case, will be the molecular interactions that occur in the fluid, in the gas. And for this, we use something that we call the virial equation of state. Okay? And the virial equation of state is basically, if you can see, this first part is the ideal gas law, plus a term that helps us approximate and add up the changes in the molecular forces that are occurring in the system and how they affect pressure and temperature. So in here we use this coefficient, and this is called the virial coefficient, and is a correction factor to account for attractive forces between gas molecules, because they become significant at pressures higher than 2000 kilopascal. Normally, this coefficient will be negative, and the units that are used are cubic meters per mole. Now, this is normally not used in industry. In industry, ideal gases and the virial equation of state, such as these ones, might be too primitive if we are to use a solver or a simulation process. And what is used in industry is mainly cubic equations, which are closer approximations to the reality. And one of the most popular cubic equation is the van der Waals equation of state. And in this case, we have the example of the cubic equation, and in here we will introduce other constants, which in the equations would also predict liquid volumes. So we can see that this equation becomes quite complex and difficult to solve by a numerical order or just by hand. However, now through computers and through simulation, we're able to solve these type of equations, and that's the preferred way in industry in order to approximate the non-ideality of the system. As well, because sometimes in industry we will have so often pressures up to 2000 kilopascal or higher, that 5 times the atmospheric pressure, and we want to use this type of equations to approximate it. So now we give an example of calculating the temperature, the enthalpy change. So let's try to work out this example. So we have 5 kilograms of water are to be heated and compressed from 298 kelvins and 101,300 pascals, so 101.3 kilopascals, to form a vapor at 450 kelvins and 600 kilopascals. So calculate the energy that you will need in terms of enthalpy. Okay, what will be the energy that you need in order to convert 5 kilograms of water from these conditions to those conditions. So in order to know the amount of energy that you will need, then it's basically going through the chart, the 3D chart that we saw previously. So we're going to fractionize, first of all, heating, after that compression, and how the energy that is needed to go through that systems in order to arrive from point A to point C, and in an ordered way. So in here we'll have some data. So the heat capacity of the liquid is given by this linear approximation, Cp as a function of temperature, in order to be able to substitute it in the equation that we saw previously, Cp dt. And the heat of vaporization at 373 kelvins is this one. So remember that the heat of evaporation is the heat that is used in the saturation line in order to go from one state to another, if you remember. The heat capacity of the vapor is given by this approximation at this pressure. And we are given, in this case, the virial coefficient and its derivative with respect to temperature are these ones. So in this case, we are dealing with a gas at higher than 500 kilopascals, so 600 kilopascals. So we are going to use the equation of state with the virial coefficient, in this case, in order to be able to solve this numerically. Okay, so why don't you think about it for 5 minutes and try to solve this problem.
Many years ago. Have you got your thermal? Did you have the red thermal? It's got literally all the end of it. I've still got mine. Now we need the form. That's exactly what I said. This is like the exam all over again. Always make things complicated. I haven't forgiven that. Did you show room? Did you show room? Yeah, you did. He's getting it. Exactly. He's waiting for the one. Today. Do you have the formula? We do what? Yeah, I'll see it, and then you apply the formula. What's the CP formula? It's H with the H instead of but it's H2 minus H1. So it's that formula, but it's H2, because normally it's still a H, obviously H2 minus H1. And then put it into that formula, you've got CP, and you apply CP to the viral one. Compare the difference in the units like yeah, exactly, that's why you think it's in the text. Trust me, mate, I've got just tell what you don't look stupid. Are you sorry? You should be able to do it as well. What's your background? No, yes, I mean, you don't thermodynamics. Only in school. Did you not? What school was this? Are you sure this was at school? Did you not teach you dynamics? In mechanical engineering? That's what I mean, I need to show you, I don't know how to do this. Speaking materials for what is fabric. How do you do mechanical engineering and dynamics? Does that know? How is that possible? It's literally the fundamentals of mechanics. So what did they teach you instead?
I think, yeah, that seems to be it.
You must have done fluid instead of that. It comes up in every engineer. It's so essential. Best semester, how many?
Second year.
Oh yeah. Best semester of second year. Sorry, I don't like the semester. My 10th semester. I'm upset. I'm getting Tell me about it.
Liquid to gas.
Right, so just to help you out for the calculations that you are doing, so we need to use this formula that we saw before, and then we need to look at the 3D chart that we saw at the beginning, right? So we want to move from point A to point B. So what we're going to do is we're going to move at constant pressure through the temperature, going to the saturation line, add the heat of vaporization, move at constant pressure through the vapor line or the gas line, and then increase the pressure of the vapor line to arrive to point B. So basically we are taking into account like if you had a heat exchanger and a compressor together. That's essentially doing this, right? So in this case, we basically move at constant pressure throughout the temperature line in the liquid phase. In the liquid phase, we said that the changes of volumes are equal to 0, so therefore dH equals Cp dt. We have an equation for Cp. We substitute that equation on the Cp and we integrate. Once we integrate, we put the initial and final values and we obtain the enthalpy for that part, for the liquid. We add up the enthalpy of vaporization and then we take the enthalpy for the vapor phase. For the vapor phase, there is a change of volume, so we'll need to take the virial equation of state that we just saw at the beginning. And in here in the virial equation of state, we are given B already, in the approximation. So we basically use the ideal equation plus the correlation parameter. We input that into the equation and we calculate CPDT plus what we have. And finally, for the compression part, we basically calculate the energy through that compression. So I will explain that afterwards. But please do this part first. So let me see, is that clear? No? Not clear at all? Okay, again. Right, so do you understand this chart, how we are moving here? Okay, that's sorted. So the first part is that we are going to move from A to B in stages, okay? So in order to work out the equations, we are going to first assume constant pressure in the liquid and change of temperature. If we go back, the changes in all the enthalpy needed will be equal to CPDT plus the changes in volume with respect to temperature and the changes in pressure. In this case, we are saying constant pressure, and we have a incompressible fluid because we are in the liquid side of the chart. So all these terms goes to 0. So we end up with dH equals CPDT, right? In the example, we are given an equation for Cp. The heat capacity of the liquid is given by this equation. So therefore, dH equals 4024 plus 0.577 T dt, right? So if we integrate dH, so we're going to integrate this equation, right? So the integral of that equation will basically give us delta H equals 2 4024 T what's that? T squared. Yes, over 2. Then we have the initial temperature and the final temperature, and therefore we are able to substitute that. Well, this will be for T1 and T2. We are able to substitute that into the equation and get the delta H. Is that right now? So if we do that, we basically go through this process and obtain this energy from solving this equation. 316.3 kilojoules per kilogram. Once we substitute all this. Now, we have moved through the chart from A to here. So at the moment we're here, right? So now we want to take into account that heat of vaporization that was given to us in the example. Heat of vaporization is this 2,256 kilojoules per kilogram. So therefore, the delta H of vaporization, and we'll just take it like that. We don't need any other calculation but to know the value, joules per kilogram. So now we have moved from here to here. Okay, we have the energy that we need to be to this point. Now we need to move from here to the temperature that we want to take the fluid into. So we need to again come back to the equation that helps us define how much energy is needed. In this case, we are in the vapor phase. So that means that this is a compressible fluid, and we therefore will need to take into account this part of the equation. In order to help us integrate this equation, we said that we needed an equation of state to substitute volume here. So we are going to use the virial equation of state. And the virial equation of state give us a relationship of V1 over M RT over P plus B. So that's a relationship that we derive from the virial equation of state. So we need to substitute this V in here, in this equation, and then derive the equation. So if we do that, dP over dt, in this case we have this correlation, then we are not going to go through this mathematical solution, which will take us a lot of time and a lot of algebraics. And we basically just use the relationship that was used for this type of mathematical approximation. So in this case, we are dividing the terms, and we're basically integrated dP as well in the pressure. In this case, no, this is for compression. Here. So we basically take the virial equation of state and we move towards that volume. So let's go into the sensible heat. Ah, right, yes. Okay, here there's something that I forgot to say, is that in this case, how we are moving towards the curve, we are basically moving, taking into account a steady, a constant pressure again in the gas phase. Yes, here. Right? So we're at constant pressure in this part. So therefore, we're taking it out this part of the of that.
5 enthalpy.
So then we'll end up with dH Cp dt as well for the gas, because instead of moving this way, we're moving straight on this curve to take out and simplify the calculation. So we don't need to go through this integration right now. Okay, is that all right? So therefore, we move again through using the same approximation, dH Cp dt, even though we're in the vapor phase, but we are standardizing pressure. And we arrive to this point, okay? And then now, yes, we go and we look into the compression part, where we take the virial equation of state, and therefore we use the approximation to take into account changes in pressure. So temperature remains constant in this case, and we derive the equation with respect to Tp. Okay, so V Tp in this case. Since delta T changes in temperature are 0, this goes out, VdP. We substitute V from the virial equation of state, and we integrate with respect to dP. Right? And then, once we have all of them, so we have the energy needed from here to go from A to B. the energy needed to go from B to C, the energy needed from C to D, and then the energy from D to F. We add them all together, and that's all the energy that we need to go from A to B, to this point. And that's how we solve the system. Is that all right? Any question?
Can you just come back to the solution then?
So if we go back to the solution, you have this in Blackboard, so you can go later on by yourself. So we have the CPDT through the liquid, constant pressure, evaporization, which was given to you, evaporation, sensible heating of the vapor, basically, again, integrated the same equation at constant pressure, and finally, doing the compression part, which is, lost this slide. Which is integrating the virial equation of state with respect to pressure, and that gives us the energy in order to do the compression. We add them up, all the enthalpies together, and then we take into account 5 because it's N, and we always say N is the moles, and in this case we say 5 moles, and that's the energy that we need in order to convert N moles from one state to another state. So basically, N moles of water going through a heat exchanger and a compressor. And that's basically the use of enthalpy to help us define these processes. Those could be, if we go back to the first thing, this could be a fluid, a oil fluid going through a heat exchanger, a compressor, and we are having changes in pressure and temperature. We want to define how this will be changing. And then through the enthalpy, we're able to know how much energy is needed, how much energy is out, and basically what is the state of the fluid going through the system, which is wonderful in terms of engineering. Using the first law of thermodynamics. Now we need to put another variable, which now is the entropy. And look how the entropy will play out in here, but I think we'll do that next Monday, right? So you have the slides in there. Something that I forgot is I didn't ask who, I would like to know who is a chemical engineer, what type of engineers we have here, or even if, is anyone not an engineer? Somebody that perhaps is just trying to reach out from another area. So can you raise your hand if you did chemical engineering? Okay, what other types of engineering we have? Petrochemical engineering? Petroleum engineering? Mechanical engineering? Offshore engineering? Mechanical engineering? What else? Right, so hopefully have you seen these concepts before? No? For mechanical? Or
Offshore engineering.
offshore engineering? No. So a little bit of study for you to sort of catch up, but the book that I have used is basically what I use for all these lectures, so go if you have any problems with it. But for everybody, it's just a refreshing of knowledge. And, well, basically, in my case, I'm a chemical engineer. However, I was graduated 10 years ago. And during this time, I've been working on biofuels, which is different for petrochemicals, but it's just an alternative. Who knows how successful they will be now with all the policies and everything. But anyway, in this case, I'm originally from Mexico, so I sort of have a Spanish accent. Please, if you have problems with my accent, tell me. And then hopefully I'll be able to not completely resolve it, but be a little bit slower, talk a little bit slower, do something that can help you understand everything. It's very important that you understand what I'm talking about, right? So essential, I will say. So thank you, and we'll see us next Monday. Okay, see you, bye. Fine. So fine. By molecular weight, yes. So, let me see. Was it 5 kilograms? Okay. Yes, but that's the problem, that in this case we have joules per kilogram. We are not referring to joules per mole. So since we are joules per kilogram, we directly multiply per gram, so that's joules. If it was joules per mole,
you need to check the units first.
yes, to check it. In this case, since we were kilograms, then we can directly multiply. If it was joules per mole, we have to divide by the molecular weight.
In that integration, the first integration, I couldn't get to be one. That means the end. What line is at the end? The first integration.
Well, the end, normally we use it per mole, but you can have as well M if it's per kilogram. But it doesn't. Which equation?
The integration.
Sorry, I have a message. Here?
We'll have this question.
Yeah, this. So we still multiply with
It depends on the units, because if you want to know the joules, if you want to get the thing of joules, then you put N, because you want to relate it to mass to moles. But if you get it over joules per kilogram, you don't need to take it, because you still are referring it per kilogram. So you will later on multiply it if you wanted to know the exact energy for the type of mass that you were going through the system. So yes, then this could be NCP, and then I could go through the N, and then have here as joules, and at the end I'll multiply it by N, have it in every one of the equations. It will be the same kind of approximation.
Excuse me, please, I want to ask,
Yes.
the third integration, heating the vapor.
Which integration?
The third one, heating the vapor.
In the vapor, yes. Ah, okay. Heating the vapor,
Right
yes.
here.
Heating the vapor, we said.
Yeah, this is what I wanted to
But that's not heating. That's compression alone.
Oh, okay.
Because here we heat the vapor here, and we are at constant temperature, at constant pressure. So if we are at constant pressure, we take out all these parts from the second term goes out basically from the system. So we're basically, instead of doing this, which would imply both things at the same time, quite difficult thing, we go in steps, in 1 and 2. So we do constant pressure, we take out that part of the equation, and we use Cp delta T, the same as for the liquid. And then we do compression, and we take only dP, changes in pressure, temperature constant. So we take that part. Yes, and remain with the dP. So it helps calculations, let's say.
Simplifies the
Simplifies the equations, yeah.
The notes are already uploaded on Blackboard.
All these slides, yes, you cannot see them. Oh, that's
Yes,
strange.
they're not on Blackboard.
Not on Blackboard?
Not yet, not yet, yeah. There's no illustration.
This is all I think.
Yeah, right.
Right. I'm going to check, because I thought that I had uploaded all of them, but I'll check it, and then you'll have them before next lecture.
Okay, thank you.
Okay, see you.
I have one more question. So my name is
Hello.
Cuba. So
Hi, Cuba.
I'm
Nice to meet you.
interested in some multi-phase flow in subsea pipeline for my dissertation.
Multi-phase flow, yes.
I've been looking for some software of the Olga.
No, I haven't used Solga as a.
Actually, it's not easy to find some tutorial for that
For that
Okay,
software.
right,
Do you
so-
have a supervisor? Or?
Yeah, reconciling in our pipeline engineering.
And then is he using that software?
Yeah, but
And does he have any PhD students?
I'm not sure, but I have to.
It will be good if you ask him if he has PhD students,
Yeah.
and it's likely that they will help you to know tutorials to help you go through that software. I haven't used that software myself, so I won't be able to tell you anything about tutorials on that. But what I would suggest is you contact postgraduate student, PhD students, and they will able to help you understand better that software.
Okay, that'd be helpful for me.
Yeah, so do that, and if you still are stuck on that, tell me, and then I will ask the other lecturer if he can give you some advice.
Okay, as far as I know, so on our lecture list, we have some lecture for the slugging multi-phase flow.
Yes, it's login. I think that's when does that comes in? So which one?
This one is the multi-phase flow.
Including slugs.
Yeah.
The part that I do in multi-phase flow and what I show is basically correlations to help us understand the multi-phase flow and solve it numerically using Martinelli correlation, Fruder correlation, and other types of correlation. But I don't go into going into softwares, which may be able to explain a little better that. Nigel also talks about that. When he comes around, perhaps he will be able to provide you more information on that. But on the software on itself, I'm not sure. Now, I'm going to upload the lectures for my part and Nigel's, so you can also start looking at these lectures notes if you want, and start reading them and just to see. Yes. So I'll upload those lectures as well.
One more question. So there is no any past exam on the website. So are you gonna?
Yes, I'm
upload
going to
some
check.
past
I'm going
exam?
to check to put the PowerPoint slides in Blackboard because I thought that I have uploaded them, but they haven't been uploaded, so I have to do that again. Okay.
Thank you very much.
So yes, thank you. See you. Bye bye.